Problem number 6. A vertical sluice gate is used to cover an opening in a dam. The opening is 2 meter wide and 1.2 meter high. On the upstream side of the gate, the liquid of specific gravity 1.45 lies up to a height of 1.5 meter above the top of the gate. Whereas on the downstream side, the water is available up to a height touching the top of the gate. Find the resultant force acting on the gate and position of center of pressure. Find also the force acting horizontally at the top of the gate, which is capable of opening it. Assume that the gate is hinged at the bottom. So first of all, our first step is to understand this problem statement. This problem statement is a lengthier one, okay, but still we can understand it step by step. First of all, we have to understand that we are talking about a vertical sluice gate that is used to cover an opening in the dam. If starting from this top, this hatched line you are going to be see, if you are going to be see, then it is like a wall of the dam that you are going to be constructing to stop the water just upstream of it. If river is flowing in a particular direction, you must be clear with that. And let's suppose if a certain channel is there for the water, like a river or canal, if it is going to be flowing in a particular direction, and vertically we are going to be construct a wall that is going to be obstruct the flow of the water. Then on upstream side, mean the towards the if we talk about the direction of the flow, then towards the direction of the flow, that will be the downstream side, and at the back of the flow it will be upstream side. It will be the same for all of the cases. Whenever we talk about any device or any structure that is constructed between any between the flow of any water in canals or in rivers, like, so if this is the particular case, then upstream side will be at the back side, okay, in which the direction is there. So towards the direction of the flow, that will be the downstream side. So if we are going to be follow this and we talk about a dam, a smaller dam in which we are going to be constructing a wall, then this wall is going to be obstruct the water behind of the flow of the water and behind that wall. And if this is the particular case, then the water is going to be rise up in this channel. And if it is going to be raised up, then this level of the water is going to be specified as an increased head of it. And this head is also given over here. Okay, so if this is the wall of the dam, and this wall of the dam is going to be connected with the other part of the wall of the dam at on the other side of the flow of the water, mean towards the bottom of the river inside the depth. So here you can say that both of these walls, top wall and bottom wall, those are going to be connected with each other with a sluice gate. Okay, mean an opening has been left between the walls, the upper wall and the lower wall of the dam, and in between this opening is going to be filled with the help of a sluice gate. This sluice gate is a device that is going to be used within the dam wall of the dam just to control the flow of the water between the downstream and upstream. If downstream the water level is, let's suppose any water level is going to be maintained over here, okay, like this, so it will be a downstream water level, and here you can say it is an upstream water level. So upstream water level and downstream water level is also going to be having a certain difference in between the heads. So if this is the particular case and you want to control it between the heads of the upstream and downstream, then you need to allow some water from to flow from upstream to downstream, or you need to be obstruct the flow of the water, stop the flow of the water from flowing toward from the upstream to downstream. So for that you need a certain device to control the movement or flow of the water from upstream to downstream side of this wall of the dam. So for this particular case you need this particular gate. Okay, so this gate individually is going to be act as a particular surface that is going to be submerged within the body until or up till a certain depth. Okay, so if we are going to be considering the case and we are going to be analyzing our sluice gate only, then it is going to be a case when our body is a submerged body. And for the submerged bodies, if we want to determine the pressure on this fluid, is this sluice gate, or we want to be determine any other parameter, we can determine very easily. Now we come to the other input data of it. Here the input data starts from here. The opening is 2 meter wide and 1.2 meter high. So high is very easy. Okay, so this is the depth, you can see 1.2 meter. Now what about the width? So width mean it is in the third dimension. Okay, so on the other side, like this. So inside the paper, what is the dimension? This will be the width of it. Okay, so inside it, this width is equal to 2 meter. Okay, so once we are going to be in our calculations, if it is required, the width, if it is required, then it will be in a transverse direction, lateral direction, and in the lateral direction you can consider the width. So it will be inside the plane or inside the paper. Okay, so it will be 2 meter. So 2 meter wide this sluice gate and 1.2 meter high along the depth of the dam, of wall of the dam. So it will be 1.2 meter. On the upstream side of the gate, the liquid of specific gravity 1.5 lies up to a height of 1.5 meter above the top of the gate. So if we talk about the top, okay, so this is the top of the gate, this is bottom of the gate. So top of the gate is going to be having a level of 1.5 meters from the surface of the water towards the upstream. And here the liquid is not water, it is and the liquid with the specific gravity of 1.45. So you have to keep this thing in your mind while calculating the pressures on the sluice gate, that on upstream side, whatever the fluid is exerting a pressure on this sluice gate, it will be not water, so it is having a 1.45. So you need to be this multiply this specific gravity with the density of the water to get the required value for this fluid and for to calculate the pressure exerting on the sluice gate on upstream side. Whereas on the downstream side, the water is available up to a height touching the top of the gate. So just the top of the gate water is available. Mean above that the water is not available. Mean the downstream side water level is going to be starts from the top of the gate. So here you can say this is the level of the water. You need to mark that. Okay. So on downstream side of the water, we were talking about the downstream side. Okay, so here it is going to be coinciding with the top of the sluice gate, this downstream side water level. Next is to find what you need to find. So here we are ending up with the input data. So after the input data, if you are going to be sketching it out or you imagine the case, then one by one you can draw the schematic diagram of the problem. This will be the first step towards the solution. Once the given statement is with you, then depending upon the situation and the cases and input data, you will be able to draw a schematic diagram just to be right about all of the heights, all of the widths, and all of the situations and cases, and the devices, or you can say the surfaces, will be given to you. So all of the objects you are going to be and dimensions you are going to be draw schematically, and then you are going to be start with the solution. So here you need to find the resultant force acting on the gate and position of center of the pressure. So two things you need to be determined: resultant force. Okay, so resultant force mean the force that is going to be exerting from the upstream side liquid on the sluice gate and from the downstream side water or the liquid towards the gate. So whatever the resultant force mean, net force is going to be applied on this gate, you need to be determined. And second one is the position of center of pressure. So obviously once the forces or pressure will be there, so center of pressure formula is also with you, you can determine it very easily, and we will do it. Find also the force acting horizontally at the top of the gate, which is capable of opening it. So from the downstream side, if the water is exerting a certain force, so you need the resultant force at the top of the gate, so that you can open it by applying that particular force. Assume that the gate is hinged at the bottom, and we are considering a smaller hinge at the bottom of this gate. Okay, so what is the purpose of this hinge and where it is going to be used during the analysis of this problem statement, we will see that. So starting from the solution, we have width of the gate 2 meters. Depth of the gate 1.2 meters. Area, you can calculate if width and depth both will be with you. V into D, it will be 2.4 meters square. Specific gravity of the liquid on upstream side. That is very important. You can add over here. Specific gravity of the liquid
specific
on
gravity
upstream
is with
side
you
of the
for
gate,
the liquid on
it will be
upstream side,
1.45.
then you can multiply it with
these
the density of the
values
water,
with 1000, and you can get 1450 kg per meter cube, specifying it as rho 1. Mean on upstream side liquid is going to be represented by rho 1. Okay, all of the 1 subscripts are for the forces and for the dimensions and the densities on the upstream side. So we are going to be represent all of the upstream parameters with the 1 subscript. So here F1 is the force exerted by the fluid of specific gravity 1.45 on the gate, okay, on the upstream side. F2 is the force exerted by the water on the gate, mean from on the downstream side. You have water. So the force F1 is given by, you have the formula, F1 is equal to rho 1 G into A into H1 bar. So H1 bar mean the depth of, or you can say the center of pressure, center of gravity of this particular object that is submerged within the liquid from the upstream side liquid level. Okay, so that will be H1 bar. So rho 1 we have already calculated, 1450. H1 is the depth of the center of gravity of the gate from the free surface of the liquid on upstream side. Okay, so that you need to be mentioned all the time. Here they have differentiated upstream and downstream by considering a word of liquid and water. Okay, so if they talk about the liquid, mean upstream side. If they talk about the water, then downstream side. But you can also add over here, okay, that depth of the center of gravity of the gate from free surface of the liquid on upstream side. Okay, so it will be 1.5, that is the depth of this sluice gate from the top. Okay, it will be 1.5, and further you need to be add up the center of gravity. The center of gravity of this rectangular body will be at the half of it, h by 2. Okay, so it is total 1.2 dimension, and half of it will be 1.2 divided by 2. It will be 2.1 meters. So in this way h1 is known to you, and this formula to calculate the pressure on upstream side of the gate, and area is already calculated. G is 9.8 and rho 1 is already calculated. Now what you can do, you can just input the values in the formula and you can get the answer, that is 71691 newtons. That is the force exerted on the sluice gate from the upstream side. Now similarly on the downstream side, the pressure forces, here you can see the F1 we have calculated. Now F2 we need to be calculated. So F2 will be equal to rho 2G AH2 bar. So rho 2 is simple thousands because water, G is 9.8, area will be the same because the gate is same, and the H2 will be now it from the downstream side. This extra head is not going to be considered because it was from the upstream side. Now downstream side the water level is here, and from here directly it is actually this downstream water level is starting from the top of the sluice gate. So just half of the dimension of the sluice gate is going to be considered over here, and it will be 1.2 total height of the gate divided by 2. It will be 0.6. So if you are going to be inputting your values, it comes out to be 14126. So very smaller values. Here is 71,691 and here 14,000. So 71 and 14, you can see a lot of difference is there. So here the pressure are smaller and here the pressure are larger. So upstream side is going to be exerting more pressure on the sluice gate than the downstream side pressure. So comes towards the results. So our first required result was to determine the resultant force on the gate. So resultant force will be the net force that has been exerted on the sluice gate from right and left side, from upstream and downstream side. So you are just subtracting the forces exerted from both of the sides on the gate. It will be 71,691 minus 14,126. This comes out to be 57,565 newtons net force, pressure hydrostatic force exerted on this sluice gate due to the pressure of the upstream side fluid and the downstream side fluid. Now the second thing is position of center of pressure of the resultant forces. So for that you need to do some extra calculations. The force F1 will be acting at a depth of H1 steric, mean the center of pressure, from the free surface of the liquid given by the relation So if center of pressure from the upstream side you need to calculate. So for that H1 bar is going to be used. H1 steric is going to be used. That is going to be represent the center of pressure. So here the formula of the center of pressure is with us. So within this formula, H1 bar is known to us, that we have used in the analysis in the previous calculations, but Ig is needed to be calculated. Ig is the moment of inertia. So for that, BT cube divided by 12, it's a rectangular submerged body. So for that, BT cube divided by 12 is there. So you are going to be inputting your values, and in meter 4 units you are getting your answer 0.288. So H1 bar, by inputting the values, you are getting your answer as 2.1571 meter. So keep this distance with you. This distance of center of pressure is you are calculating from the top. Okay, so distance of F1 from the hinge if you want to calculate. So H1 is the center of pressure, that may be represented by like this. So H1 we have already calculated from the surface of the water, from here. Okay, so where F1 is here. Okay, so that point, this distance is HP1. Okay, so HP2 later on when we will calculate, so it will be the F2, the point of application. Later in the previous results, we have had only the physical quantity. In quantitative form, we get the result like F1 and F2, and we had answers like this. So we were not known about the point of application of these forces on upstream side, hydrostatic forces on upstream side and downstream side. So now if we are concerned with the point of application of these hydrostatic forces, then we need to determine the center of pressure. And these center of pressure will give you exactly the point of application of these two forces. Okay, so these comes out to be H1 equal to 2.1571 from the top surface. Okay, so this value comes out to be 2.1, okay, 571. Now if we talk about the distance of this center of pressure from the hinges, so what you need to do, this will be equal to this distance. Okay, so this can be calculated by getting the whole distance 1.5 plus 1.2 and subtracting this distance, you will get this value. So it will be 1.5 plus 1.2, you will be at the hinge, and subtracting this HP from the surface of the water upstream liquid towards the point of application of F1, the first hydrostatic force F1, and you are getting this distance. So this will be the distance from the point of application of the hydrostatic force from the upstream side towards the hinge, bottom hinge. So it will be equal to 0.5429. The force F2 will be acting at a depth of H2 steric, on the other side I have told you, this will be HP2 or H2 steric, okay, from the downstream side. So it will be can be calculated by using the same formula. This will be HP2, okay, or H2 steric. So it will be, the formula is given over here. So you have all of the values with you, just you need to be change the H2. Okay, so it will be 0.6. So you are inputting the values and you are getting your answer as 0.8. So it will be from the level of the water on the downstream side. So if you want to be, you need this distance from the bottom hinge. Okay, so this distance will be the total distance, 1.2 minus HP2. It will be 0.4 meters. The resultant force, that is 57,565 Newton, the net force, resultant force acting on the gate will be acting at a distance given by. So if the forces, individual forces, where those are acting, the point of application of the individual forces will be with you, then for the resultant you can also determine. So how you can do that? You can do that, the resultant force, or you can say that FR multiplied by the distance. Okay, so it will maybe y kar le aap is distance ko, you can say that it is yr resultant. It will be equal to the forces acted by the moments produced by the individual forces. So it will be F1 into Y1 plus or minus, whatever the case is, clockwise or anti-clockwise depending upon that. So it will be F2 into Y2. Okay, so in this way you can say, you can use this equation. So the moment produced by the resultant will be equal to the individual moments produced by its components. Okay, so net force is with us, so you can have this equation. So here on the left hand side you may have the resultant force multiplied by the distance. Okay, and this distance may be yr. Okay, mean the moment arm produced by the resultant force, and this distance will be equal to the moment produced by the individual force multiplied by its moment arm, and the force second one F2 multiplied by its moment arm. Okay, that we have calculated center of pressure 0.4 from the bottom hinge. So if you are going to be consider the F1 multiplied by this distance, so this force will be there, this moment, the moment produced by this force F1, that is multiplied by this distance from the bottom hinge. Okay, so this will be the Y1, F1 into Y1, and it will be clockwise direction. Okay, so mean one direction, so other direction F2 will be in opposite direction. So F2 is going to be produce the moment in the opposite direction. So it will be like this, your F2 is going to be produce the movement in the other direction, and this will be Y2, mean its moment arm about the hinge at the bottom. So in this way you are getting the moment arm for the resultant. Okay, yr. So it will be 0.578 meter above the hinge. So above the hinge this resultant force is going to be produced, the force or the moment equal to 0.578. So it will be the center of pressure of the resultant force from the bottom hinge. Okay, now third one is to be calculated, force at the top of the gate which is capable of opening the gate. Let F is the force required on the top of the gate to open it, as shown if we are going to be see this figure. So in this figure, this is the force that if we are going to be considering, that is applied just at the top of the surface, this sluice gate surface. So we are going to be representing it with F. So how to get this F? Taking the moment of F, that is the resultant force, and that is caused by the components of the forces, mean the forces exerted on the gate from the upstream side F1 and from the downstream side, that is F2, about the hinge. Then again the same equation we can use, but here the distance is not needed to be calculated, here the force is needed to be calculated, the resultant force. Okay, so here you can say the resultant force multiplied by its moment arm from the hinge will be equal to F1 and F2, those are the components of it, mean the internal forces, individual forces. So these individual forces within these systems are producing whatever the movement is going to be producing about the hinge, that will be equal to this resultant force that needed to be applied at the top of the gate. So here the resultant force is going to be changed, and here you are getting the answer as 27,725.5 newtons as an answer. So this force is required to apply at the top of the gate to produce it, to open it, capable to open it, to control the flow of the water through this sluice gate. So this is it for this particular numerical. Now problem number 7, a tank with 2 meter is full of water. You need to find the total pressure on the bottom of the tank as shown in the figure with the particular dimensions. Second, you need to determine the weight of the water in the tank, and thirdly you need to determine the hydrostatic paradox between the results of A and B. So this paradox is very easy. If both of the answers will be with you, then the difference will be there, and it is going to be confirm the hydrostatic paradox. Okay, so here this dimension 3 meter is from the surface of the water and till here. Then this dimension is 0.4 width of this top width of this tank, and the bottom width of this tank is 4 meters. And for the bottom part the height is 0.6. So So it's very easy to calculate. You can do it by yourself. Okay, no longer calculations are required. For the total pressure on the bottom of the tank, you have the height, total height 3 into 0.6. Okay, so you can get that, and you need to multiply it with the base area. So this base area will be 4 meter multiplied by 2 meter. 2 meter is the width. So width will be in the inside. Okay, I have told you this dimension width is always inside the paper. Okay, so for that also, for the upper part and for the bottom part. Okay, so this total width inside the paper, it will be 2 meter. So width is 2 meter for this particular tank, and if you are going to be multiply the hydrostatic pressure, mean this head, pressure head, with the base area, you will get the total pressure on the bottom of the tank. So total height will be 3 meter plus 0.6. It will be h, and you are multiplying it with the base area, it will be 4 meter multiplied by 2 meter. That is the width. And secondly, weight of the water in the tank. So for the weight, you have the specific gravity, it's just water. Its standard constant will be there. So if you are going to be multiplying it with the volume of this tank, then you are getting the weight. Okay, so weight per unit volume. So it will be the density. So density is known to you, and volume you can calculate very easily. The dimensions are with you, and you can calculate the weight. And again, for the third part, it's hydroparadox. It's for the result, it's very easy, that the total weight of the water in the tank is much less than the total pressure at the bottom of the tank. This is known as hydrostatic paradox. So you are familiar with that, and you can get a better an idea about this paradox. Now problem number 8. It's again a very easy problem. A closed tank, rectangular in plane with vertical sides, is 1.8 meter deep and contains water to a depth of 1.2 meter. Air is pumped into the space above the water until the air pressure is 35 kilonewton per meter square. If the length of one wall of the tank is 3 meter, you need to determine the resultant force on this wall and the height of the center of the pressure above the base. So this is the system in which you have a closed tank. So first of all, we need to close it. Okay, in this figure, you can see this is a closed one, like the second figure. Okay, so this is a closed tank, and this closed tank is going to be filled with water at a height of 1.2 meters. So here you can say this is the level of the water, where the water has been filled till a height of 1.2 meters. Total height of the tank is 1.8 meters. Okay, this is given over here, 1.8 meter deep tank. It contains water to a depth of 1.2 meter. Is also, you can sketch it out very easily. Okay, if the closed tank, you are going to be first of all sketch out, and then you are going to be sketching the level of the water, and you are mentioning the dimensions for the water depth 1.2 meter, and for the total depth of the tank is equal to 1.8 meters. Now next is, air is pumped into the space above the water. Okay, you can see over here 1.8 meters minus 1.2, it will be 0.6 meters left above the surface of the water within the closed tank. That surface, if it is not going to be filled with the air or any other liquid or any other kind of the fluid like gas with the different pressure than the atmospheric, then we are going to be considering that our water is going to be enclosed within the closed tank under the atmospheric pressure. If atmospheric pressure is not there, then whatever the pressure is, you need to mention. So here it is mentioned that this pressure of the air that has been filled at the top of the water within the closed tank, that pressure is not equal to atmospheric pressure. That pressure is 35 kilonewton per meter square. Now the specific value of the pressure is given over here. So your air has been pressurized within the closed tank above the water equal to that particular value. Now if the length of the one wall of the tank is 3 meters, okay, then what you need to determine, the resultant force on this wall and the height of the center of the pressure above the base. Okay, so this you need to be determined. So here you have the water. Okay, first of all, you need to determine the resultant force on this wall, on one side of the wall. Any wall you can consider, like right or left. So in this case, let's suppose if right side wall of the tank has been considered, then it is required to determine the resultant force due to the air and due to the water applied on this particular wall of the tank. And secondly, you need to determine the height of the center of pressure above the base. Okay, so this is the base. Then starting from the base, what is the distance of the pressure that has been exerted on this wall, and the center of pressure is needed to be determined. So for that we have already calculated this type of the system. Okay, but with different kind of the fluids, liquids. One water and oil has been placed above the water, and we have calculated or we have drawn the diagram, pressure diagram, and from the pressure diagram we have calculated the forces in terms of resultant forces exerted on a particular phase or particular part of the container, or like this. But here the only difference is that other than the water, liquid is going to be filled along in a closed tank along with the gas. That the fluid is gas, and other one is the liquid. So liquid and gas has been filled within one container. So how you will do that? It's very easy. Let's suppose if it is required to determine the resultant. So your resultant pressure or the force will always be equal to the pressure applied or the force applied by the air plus the force applied by the water on a particular wall. So if it will be the air, it will be 189, and if it will be water, it will be 21.19. Okay, so height is given, it will be 0.6. Okay, so you are multiplying the force, pressure 35, multiplying by its own distance, that is 0.6, and on the other side, if the water is required, then for the water it will be 21.19. That is the force exerted at the center of pressure of this triangular area. Okay, and also one triangular area is going to be exerted by the air. So one resultant one component is from the air and one component is from the water. So you are adding up and you are getting to 10.19. So if x is the height above the base of the center of the pressure, through which are x. So if we talk about where this resultant is going to be acting, this distance from the base. So individual distances we are known. It will be at the center of gravity. Okay, your air is going to be acting as a base pressure. Okay, so this will be a base pressure or the base load that has been acting throughout the container from the top till the bottom. I have told you this in the previous numerical problems, that once one liquid has been placed above the liquid, then its pressure is going to be considering constantly applied throughout the base, starting from the top. And for the bottom one, liquid or fluid has been applied starting from its own surface till the base. So from this to this, the air pressure is going to be give you a constant value like a base load or base pressure. So this base pressure has been applied on the bottom of this container, that is constantly will be going to be applied. It is not going to give you a variation. But for the water, it is going to give you a variation. It's not a base pressure. Okay, so it will be a triangular, you can say variation. It will give you a triangular variation. So in this way, or linear variation. So in this way, your air is going to give you a rectangular distribution of the pressure, and for the water it will be a triangular distribution of the water. So here you are getting your center of gravity for the R air, the one component, that will be half of the height of the container, and your R water, the pressure exerted by the water, it will be acting at 1/3 from the base. Okay, so if the individual movement arms will be known to you from the base, from the bottom of the container, then this resultant can be determined. On one side the resultant, on the other side will be the components of it, and in this way the x can be determined. It will be 0.85. So it will be the height of the center of pressure above the base that is going to be exerted due to both of the liquids, gas and water, on the base of the container. Now problem number 9. The angle between a pair of the lock gates is 140 and 140 degrees, and each gate is 6 meter high and 1.8 meter wide, supported on hinges 0.6 meter from the top and bottom of the gate. If the depth of the water on the upstream and downstream sides are 5 meter and 1.5 meter respectively, then you need to estimate the reactions at the top and bottom of the hinges. Okay, so what is the cases? Here the case is that if we talk about the plan view of the flowing water, okay, and we talk about this first figure on right hand side, left hand side, then this is the direction of the flow of the water within this channel. These solid lines are going to be represent the border lines or boundary of the or the embankments of any channel, and this is going to be show you the direction of the flow of the water within this channel. So if this is the particular case and this is the center line of the channel, then one gate has been constructed. This is the plan view of the gate. So actually inside the plane it will be the height, okay, that is going to be represented in the other two figures on the right hand side. So here on the left hand side you can see this is the plan view, okay. So within the plan view you can see that how the gates has been constructed, or you can say installed. So here the gate has been installed in such a way that from the center line those are going to be making an angle equally 70 degrees at the for the one side gate and 70 degree for the other side gate. So total angle between these two gates will be 140 degrees. So these are not perpendicular to each other, and these are not mean to say exactly having a certain angle. So these are at angle, okay, from the center line of the flow of the water, flow of the channel. So it will be 70 degrees from here to here, okay. This angle is 70 degree from the center, and from the other side it is also, for the other gate it is also 70 degrees. So total will be the 140 degrees. So in this way you are going to be understand the values, okay. So now what about the other things? So here we have dimensions 140 degrees. Then each gate is 6 meter high and 1.8 meter wide. So wide only we can see, the width we can see in the plan view, okay. So in the plan view we can see it is 8.8 meter. Now what about the height? Height we can see in the front view, okay. So in the front view we can see the height that is 1.8, okay. So total height of these gates are 1.8 meters. Supported on hinges 0.6 meter from the top and bottom of the gates, okay. So those are supported at the hinges. So here you can see one hinge that is just you can say located over here, and one hinge is located over here. So at the top, from the top of the gate, this distance of the top hinge is 0.6 meters, and from the bottom this distance is 0.6 meters, okay. So these hinges are going to be located over here. So in between you may have the other distances, but this is the total 6 meter height, okay, total height. And out of this total height of the gate, 0.6 meter from the top and 0.6 meter from the bottom has been left for the hinges. So hinges are located over here at the top of this gate and at the bottom over here. If the depth of the water on the upstream and downstream sides are 5 meter and 1.5 meter respectively, okay, now how to sketch it out? So once the height of the gate is with you and you have marked the hinges, okay, where those are located, the top hinge and the bottom hinge. Here also you can say this may be the top hinge and this may be the bottom hinge, okay. So this is the particular case. Then what about the upstream water level? This upstream water level is equal to 5 meter, okay. This D is equal to 5 meter, that has been mentioned over here. And for the bottom downstream side, this level of the water is equal to 1.5 meter. So what you can say, you can mark an additional in this diagram, you can mark the level of the water and you can write this is upstream side, okay. And here you can mark this point and you can mark it is a downstream side, okay. So in this way what you need to determine, if you have understood all of these sketches, okay, then what you need to be determine, you need to determine the reactions at the top and bottom of the hinges. Mean this reaction at top hinge RT and this reaction at the bottom hinge, that is RB. This you needed to be determined individually, okay. So if it is required to determine the resultant of any system of the hydrostatic forces, okay, then we can determine first of all the individual forces and then you can determine the resultant force. If the individual is needed to be determined, then first it is required to determine the resultant, and from the resultant you can move towards the determination of the individual forces of this particular system. So for this case you can go towards the next slide for the solution. If you have understood the sketching of these diagrams in this system, then we can some more things you can see in this diagram, okay. That is F. F is the force exerted by one gate on the other and is assumed to act perpendicular to the axis of the lock if friction between the gates is neglected. So first of all we need to determine this, or we need to be mention this F. What this F is? This F is the force exerted by one gate to the other. Okay, so here you can see these two gates are not going to be give you a horizontal or actually the vertical dimensions. Those are inclined to each other. Those are connected with each other inclinedly, and the angle is also given. Now a certain force is also going to be exerted by the gate, one gate to the other, from this to this and from this to this, in both of the ways. So here if this forces need to be determined, that we can determine in terms of F. Okay, that will be the perpendicular to the axis that is be at the connection point. Okay, where the connection of these two gates be there. Here this the horizontal axis be there. So this axis perpendicular to this axis, normal to this axis, this force has been applied. That is the force exerted by the one gate to the other. Okay, next is what P is. P is the resultant of the water forces P1 and P2 acting on the upstream and downstream faces of the gate. Okay, now we have this P1, that is the force exerted by the water from the upstream side, and P2 is the force that has been exerted by the on the gate on from the downstream side. So our P is the resultant of these two forces, the water forces, hydrostatic forces on the gate. Okay, and what R is the resultant forces of the system where the hinges are going to be applied, the reaction forces on the gate, RT and RB on top and the bottom hinges. Okay, so that will be the R over here. How this P is going to be acting, you are familiar with that. If any submerged body is there, then the hydrostatic forces are always going to be acting normal to that particular surface. We are familiar with this hydrostatic law. Okay, so this will be at 90 degrees in all of the cases, our hydrostatic forces, and this will be this force of the one gate applied on the other gate will be normal to the axis of the connection contact point of two gates. That will be normal to that. Now this R will be going to be show you the hinges. Okay, so it will be going to be applied along the depth of the gate, and it will be going to give you the point of application. Mean what is the angle of that? That angle will be anyone, we will calculate it later on, but it will be the resultant of the force RT and RB. RT is the reaction applied by the top hinge of the gate, and RB is the reaction applied by the bottom hinge of the gate. Now, first of all, we need to be calculate the system of hydrostatic forces. Okay, we are interested in that. So for the hydrostatic forces, if we want to be solve this system, then we need the pressure exerted by the upstream water on the gate, and then we need P2, that is the the pressure exerted by the downstream side. All of the parameters are with you, and finally you are interested in calculation of the P, that is the resultant pressure, hydrostatic pressure exerted on the gate, I mean force exerted on the gate. So in this way P1 minus P2, like the previous numerical problem. Okay, so if P is with you, then the point of application of this force about the one reference point, that is O. Okay, this O is at the bottom of the gate. This point you are first of all selecting. So if this point O is with you, then about this point you can find out the moments produced by the resultant P and the individual forces P1 and P2. And in this way the point of application of the resultant hydrostatic force you can determine. It will be 1.782 from the bottom. Okay, so in this way the resultant can be determined for the hydrostatic forces, point of application of the resultant. Now, if you are going to be consider F, R and P are coplanar, and why we are considering that? Because we are neglecting the frictional forces. If frictional forces are going to be considered, then you may not say that your F, R and P are coplanar. So you are familiar with this geometric laws. So if you are going to be consider neglecting the frictional forces, then F, R and P can be considered as coplanar. If this is the particular case, then they will meet at a point. Okay, so here you can see, so here, here and here. So these are coplanar forces, then those are going to be meet anywhere at one point. And since F is assumed to be perpendicular to the axis of the lock on the plane, both F and R are inclined to the gate as shown in the figure. with an angle of 20 degrees. So that F is equal to R. So here you can say that your angle formed by the force with the gate, it will be 20 degrees because it will be 70 degree total angle, 90 degree from the axis, and left will be the 20 degrees. Okay, so 20 degree will be the angle. In this particular case, if both are going to be making the same angles, R and F, then those will be going to give you the same answers. Your F will be equal to R. So in this way you can say that whatever the value of the P you have calculated, it will be same as of R, and whatever the x distance you have calculated for hydrostatic forces, it will be same for the resultant of the hinge system RT and RB. So if R is coplanar with P, it will act 1.78 from the gate. Okay, so in this way you need to be take the moment about the bottom hinge respectively, and you will get RT and RB in both of the cases. Okay, first you can calculate RT, and then by subtracting from the total R you can get RB. So individual forces can be determined. So these are the simpler, you can say sigma fx is equal to 0 you are considering, and you are getting your answer. So in this way you can solve this numerical problem, and finally you can calculate RT, this reaction applied by the hinge on the wall, and the reaction RB that is applied at the bottom of the gate from the hinge towards the wall. Next is problem number 10. A rectangular plane surface 2 meter wide and 3 meter deep lies in the water in such a way that its plane makes an angle of 30 degrees with the free surface of the water. You need to determine the total pressure and position of the center of pressure when the upper edge is 1.5 meter below the free water surface. It's a very simple example with an angle. If an inclined surface submerged within the body is given to you, then what you need to be determined, first of all you need to determine a plane surface, okay, that can be used as in projection of all of the center of pressure and center of gravity, just to be considered on that particular plane. If this is the plane that is shown in the figure with the help of a solid line, that is going to be coinciding with the actual surface of free water surface, okay, and it is going to be making an angle theta that is equal to 30 degrees. Okay, if this is the particular case, then for the submerged body, first of all you need to be project your center of pressure on this plane and the center of gravity on this plane and all of the dimensions on this plane, and then you will be able to find your values and you can get your answer. So you have your formula with you. In the theoretical part we have derived the formula that how this theta angle is going to be, change the formula to calculate. Rest of all of the values will be the same. To calculate the total pressure, the equation will be the same. To calculate the h bar, now after adding 1.5, that is the depth of the one edge of this inclined plane, okay, this surface that I have told you, that should start from the one edge of the inclined plane submerged in the body in the liquid till the second edge of it. This is first edge, this is second edge. So you are starting from the first edge and you are ending at the second edge. So this plane that is needed to be to project the dimensions and the points, pressure, center of pressure and center of gravity on it, it will going to be start from one edge of this inclined plane towards the second edge of this. So if we talk about the first edge, then from the first edge of this inclined plane till the free surface of the water, this depth is given, it is 1.5 meter. If when the upper edge is 1.5 meter below the free water surface, so starting point is given to you, it will be 1.5 meters. So below than 1.5 meter, what is the distance till the center of gravity? That will be an inclined distance, okay, it will not be a vertical distance. So this inclined distance can be determined by solving this triangle that is making an angle of theta, and it will be the sine component of it, that is hypotenuse, that will be you can say the base of it, perpendicular to it, and this perpendicular distance will be equal to the sine component of this triangle. So it will be 1.5 sine of 30. So this 1.5 sine of 30 will be equal to this distance, okay. So 1.5 is this distance in this equation, where h bar is going to be calculated, that is depth of the center of gravity from free water surface. So 1.5 meter is the distance from the free water surface till the upper edge of the inclined surface. Then is 1.5 sine of theta. The second term is actually this distance, okay. So this is 1.5 is the inclined distance, and this vertical distance. Okay, till here it is needed to be determined. So it is can be calculated by solving this triangle. So it will be the sine component of it, because it is theta, this will be the same, and this is the base of the perpendicular of this triangle. So this particular you can say component will be 1.5 sine of theta. Okay, so it can be determined very easily. So this inclined distance is 1.5 from the, because the total dimension is 3 meters, so half of it from the center of gravity will be 1.5, and 1.5 sine of theta will be the vertical dimension. So it will give you the total dimension from the center of gravity, okay, in this way. So this distance is known to you till here, and the rest can be determined by taking perpendicular distance of this triangle, 1.5 sine of theta. Okay. So rest calculations are very simpler. Here you have free water surface and the same inclined surface, the center of pressure needed to be determined. So for the center of pressure, again you have the formula including sine square theta into it in numerator. Okay, so other things you can calculate very easily, but what about the sine square theta, you need to be added into it. So in this way you are finally calculating. So H bar is going to be calculated by this equation, and you can calculate the center of pressure in this way. So for the inclined surface, it's very easy to calculate. Just you need to be incorporate the components with respect to the inclination of this submerged body within the fluid, within the water. So if you have any questions and regarding these numerical problems, this part, then we can discuss in online session. Thank you so much, guys.